I remember well, from the north towards the east. So this is going to vary. Okay. Whenever the stress tensor has zeros in the off-diagonal terms and just other terms in the non-zero in the diagonal, these are what are called principal stresses. Are you guys familiar? Do you remember the concept of Eigen Values?
Yeah.
Yeah, that comes from linear algebra. And Eigen Values are associated with eigenvectors. If you check the notes, I think I provided a link so you can see the description about what those means. But this is the same thing. Principal stresses in mathematical terms goes by eigenvalues. And principal directions go by principal stresses, by principal directions. Eigenvectors go by principal directions. Okay, so let's talk about these eigenvalues, what they are and what they mean. Well, the same as a vector that, notice over here that we use just one number and the others were zero because the vector was oriented in direction x, but we had the vector oriented a little bit in other direction that does not coincide with this axis. Then we'll need three numbers here to write it, right? It's going to be a combination of those three numbers. In the same way, the stress tensor, if you were to write it at an orientation which does not coincide with the principal directions, you will need 9 numbers in order to define it. So let me make a schematic about that. In general, if we have a coordinate system, let's say 1, 2, 3, and here we have an element of rock. We're going to have, as we said before, our stresses, S11. There is going to be the same stress applied on the other face that you can see. This stress in this direction, and this stress in this other direction. Those are going to be the normal stresses, correct? Let's add one more thing over here. We're gonna adopt the convention for what is positive and what is negative. We're gonna say that a stress is positive when this one is a compression stress. Notice that all these stresses are applying compression in this direction, or in direction number 2. So all of those are going to be positive. This is kind of easy to see, right? Because it looks like the arrows are pointing towards the element. So you can see that it is a compression. But it's going to be a little bit more difficult with the shear stresses. So before we go to the shear stresses, let me tell you this rule. This is our coordinate system, right? If we want to move in positive direction, we'll go in this direction along 1, in this direction along 2, or in this direction along 3. Well, this rule is going to tell me that the numbers in this stress tensor are going to be positive S11, S22, and S33. Whenever I make a displacement in the positive direction, for example, from here to here, I get to the other face, and in that face, the stress is pointing in direction opposite to the direction of the base. So you see how this one points direction opposite to 1. S22, if I go a positive direction, it will be pointing in this direction, right? If I go from here to there, positive direction 2, I will get also to S22 in this direction. And if I go a positive amount from here to there, I get to that face. S33 is pointing in the opposite direction. Probably it would be good also to say now that all of these stresses, what they mean is when I write S11, 12, this one, the first element, is the phase on which it is applied, and the second one is the direction. So let's apply this concept over here too. So this one is phase 1. Let me put this 1 over here because it's perpendicular to the vector 1. This one is phase 2 because it is perpendicular to direction 2. And the same with 3. Okay, now is when you have to pay attention, okay? Because now it gets a little bit more complicated. Now we need to talk about shear stresses. All these are called normal stresses because they are perpendicular to the plane. When we go into shear stresses, those are going to be parallel to the plane. So for example, if I want to write a shear stress, which is this one, how can we call that one? S12, right? On phase 2, on direction 2. And notice also that as I went a positive amount in direction 1, that vector now is also positive because it points in direction opposite to 2. But now it's 2 because it's in direction 2. And the same way, here in this other direction, perpendicular to it, I'm going to have S13. Let's do the example for phase number 2. Phase number 2, or let's do 3 first, it's going to be a little bit easier.
Professor?
Yes.
Why is S22 the normal force right there in the face of the block? Is that positive or negative?
This one?
The other one. The one, yeah, right there.
This one is positive because notice, we said the rule that if you walk in positive direction and you get the other face, the element should be pointing in opposite direction to this one, right? Well, if you were to walk in negative direction from here to there, notice that this goes against this direction. You will arrive to the other face, and that arrow will be aligned with the direction of the vector because you went into negative direction. If you go into the positive direction, it will be opposite. If you go into the negative direction, it will be aligned with the direction that the coordinate system has.
So both those S22s are positive?
Those are positive. And notice that all of those two are compression, right? And you need that. You need this equilibrium in this direction because otherwise, if you have forces going like this, the element would be moving and it wouldn't be in equilibrium. So let me finish with this. So which shear stress is going to be this one? S31, right? And here I'm going to have another one which is going to wait, before I draw the arrow, this one is going, well, now it's, I messed up this one. You see why? Because it's on this phase. If I walk in the, oh no, it's okay. I go in positive direction, it should be opposite to 1. I go in positive direction. This one should be in opposite to this one. And this is going to be S3, 2. And let me extend this one a little bit more towards the center. This is going to be S2, 2. And here, now I walk on direction, negative direction. And here I'm going to have S2, 3, and here I should have S2, 1. And in here, all those stresses are going to go, as we said before, S12, S13, S23, S21, S31, and S32. Shear stresses always going to go in the off-diagonal terms. Normal stresses are going to go in the diagonal terms. Yes?
Could you explain the blocking thing that you did
Yes.
before doing your shear directions?
So, the rule for writing here a positive stress, a positive number, is going to be that whenever you move a positive distance, and that means going in the directions of the coordinate system, so for example going from here to there, when you get to the other face, the arrows of stress, in order to be positive, they all should be, or each of them should be opposite to all the directions of the coordinate system. So for example, if we wanted to go positive in this direction, direction 2, we should go from here to there. But now the only stress that we see is S22. I cannot draw the other ones because they will be on the hidden face. But the one that I see is this one, and in order to get to this one, I need to go a negative direction from here to there. And in this direction, all the stresses should be aligned with this direction. So you see this one is this one, 2 is that one, and 3 is that one. So those are all positive. But in more meaningful and physical terms, notice that S22 is pointing against the other S22. So that is keeping the equilibrium in direction 2. The same with S33, if I were to draw S33 somewhere over here, and the same with S11. And with the shear stress, it's going to be the same. Notice how S31 and S13 are pointing in opposite directions, and the same as S21 and S12 and S23 and S32. Let's see why that. And in order to make it a little bit easier, let's just do it in 2 dimensions. So let's say that I have here S31 and S13. Notice these are the same as the ones that you have over there, S31 and S13. I'm just looking from the side. Without thinking about positive or negative rules, this stress over here should go up or down?
Up.
Should go up, right? And this one should go left or right? Left or right?
Right.
Right. Why that? Because the torque that you're applying with this one is also S31 and this one is S13. The torque that you apply in this direction has to be counterbalanced by the torque applied in this other direction. So this one tries to do this, but this one over here tries to do that. So only when those are the same, the solid is not going to rotate. For example, let's say that we don't have these two. If we don't have these two, the solid will rotate in direction counterclockwise. We just do like that all the time. But since it is in equilibrium, S31 has to be the same as S32. 1, 3. And this is because angular momentum equilibrium. What that also means is that when you go to the matrix, this is what is going to be called a symmetric matrix. And it's going to be symmetric because this number is going to be equal to that one, this one is going to be equal to that one, and this one is going to be equal to that one. So it's symmetric with respect to the diagonal. It's like if you have a mirror over here, this one is equal to this one is equal to that one, and this one is equal to that one. Okay, so by now we know what are all the elements of stresses. We know that in 3 dimensions, in general, we will have normal stresses and shear stresses. And the next step is going to be to simplify this. Most times, you may have to face this type of stress tensor. You need to know what it means. But for most practical applications, we're going to simplify it. And the way that we're going to simplify it is by finding what are known as the principal stresses and principal directions. So what are those principal stresses and principal directions? Let's say that you measure the state of stress at a location and you get all these 9 numbers with a given coordinate system. There is going to be always, for the stresses, a coordinate system at some orientation that we don't know but we can calculate, for which the stress tensor is going to reduce to just normal stresses. And that is what is going to be called these are going to be the principal directions